thesis defense. My name is Mansooreh Montazering, and I have been a master's student here at Concordia under the supervisions of Professors Mohammadi and Nader Khani. And my thesis is on deep learning methods for hand gesture recognition via high-density surface electromicrogram signals. First of all, I want to give an outline of what I want to talk about. I will first give an overview of the HMI devices and hand gesture recognition. And then I will do a literature review on the prior works that are done in this specific context, and I will explain about what hand gesture recognition is, specifically with high-density SEMG data. And then I will clarify my utilized data sets throughout the whole thesis. And after that, I will talk about two of the most important models that I developed for this thesis that were based on transformers and spiking neural networks. The transformer-based model was applied on two different groups of data sets. The first one was the microscopic neural derived information, which was the high-density SEMG signals, and the next one was the microscopic neural derived information that are the motor unit spike trains extracted from them. And finally, I will give a conclusion and talk about some directions for future research works. First of all, if I want to talk about the HMI devices and hand gesture recognitions, this specific topic has many applications in augmented virtual reality, robotics, exoskeletons, prosthetics, and driver assistance. Till now, many machine learning and deep learning models have been proposed to do real-time and robust automatic hand gesture recognition, but these models face some challenges even nowadays, like data scarcity, and the real-time performance. These devices cannot tolerate large delays during their work, and also many of the hand gestures have ambiguous patterns in these devices, and the models should be able to detect these patterns. So our motivations here were to design a deep learning model that requires no data augmentation or transfer learning and is able to detect patterns among a very large number of hand gestures, which is a very generalizable deep learning model, and it has a near real-time applicability in many HMI devices. So our goals was to do hand gesture recognition on both the macroscopic neural derived information and combine the microscopic neural derived information to improve the model's performance. To give a literature review on the prior works on this specific topic, myoelectric control system methods are categorized into three different groups. The oldest group is the conventional control methods like the on-off control, the direct control, and proportional control ones. These were very simple methods that used before and faced some challenges like the real-time processing, and they were unable to detect the complex movements in many hand gestures, and due to the crosstalk, meaning that some muscles are joined with each other and are connected with each other. So these control systems were not able to detect which muscle was responsible for which hand movement. Later on, researchers turned their attentions to ML models, the most popular of which were the support vector machines, the linear discriminant analysis, and co-nearest neighbors in the context of hand gesture recognition. These models are also used nowadays and have very good performance, but the challenges with these models are the need for handcrafted features, and they are very dependent on extensive trial and errors to detect which set of features could be the best feature for increasing the performance of the model, which makes it very time and energy consuming at both train and test time, and makes it very infeasible to be applied in many HMI devices. And after that, researchers proposed some models, deep learning models for gesture recognition. The basic ones were the convolutional neural networks and the recurrent neural networks. And then to address the problems associated with those two groups, the hybrid CNN RNN architectures were proposed, and finally the transformers models came into emergence. The problems with the convolutional and recurrent neural networks was that these two models only could attend to spatial or temporal features, and this was problematic, especially when we wanted to consider high-density SEMG signals that provide both type of features. So hybrid CNN RNN architectures were proposed, but these models required a lot of trainable parameters and added a lot of complexity to the network. So it made them very time consuming and memory consuming. And that is why we decided to focus on the transformers because of their input parallelization and attention mechanism to save more time and memory of the network. Here I want to explain in general why do we use the DL models rather than the conventional ML models or myoelectric control models. First of all, the DL models take advantage of the end-to-end learning, which means that there is no feature extraction required beforehand when training these models, and due to their hierarchical structures, we can simultaneously extract both temporal and spatial features. We can also use transfer learning, use other people's models for our own data sets and application. And the DL models enable automatic feature learning, and they are able to detects complex features, which is not applicable in machine learning models, because in those models we have to design the features beforehand and we have to decide which features to use. But in DL models, we can learn the features that are most appropriate in our application. And some models that use attention mechanism and transformers have input parallelization, which saves much more time in both training and testing. And also in DL models, we can ignore many of the noise and variations in high density SEMG signals, but these noise and variations can be engaged with the feature extraction process in many conventional machine learning models. Now I want to go to the next part to explain about the utilized HT-SEMG dataset throughout my thesis. I use only one set of high-density SEMG data with two rectangular grids of electrodes, each containing 64 electrodes. So I had 128 electrodes in total. These were placed on the extensor and flexor muscles of the forearm. So I had a three-dimensional data set that had 2 dimensions space and 1 dimension in time, and was acquired from 19 subjects, 5 repetitions, and 65 different hand gestures. One hand gesture was repeated twice. So I had a total of 66 hand gestures. Specifically in the transformer model, the high-density data was low-pass filtered, normalized, and windowed, and the filter that I used was a first-order Butterworth filter at 1, 5, and 10 Hertz cutoff frequencies. Here I show the formula for the specific normalization function I used. Many of the prior works used the min-max normalization, but here we showed that mu-law normalization had a better effect on making the signals more discriminative. For example, in the following image, in the left side, we can have the signals for 8 different electrodes before normalization, and after the normalization, we can see on the right side that the location and the amplitude of the signals has changed a lot, and it makes it for the network to more easily discriminate between different signals and hand gestures. In this part, I want to explain about the specific transformer-based model that I use, and I will explain about the different blocks it includes. In general, transformers were designed for sequence-to-sequence learning tasks like machine translation and text generation, but they were also widely used in computer vision and gesture recognition using images and videos, and they are known for their ability to capture the line range dependencies and input parallelization due to their attention mechanism. The main building blocks of a transformer that I used here are the patch embedding, position embedding, the transformer encoder, the self-attention, and the multi-head self-attention that incorporates multiple self-attention mechanisms and applies self-attention on each of its heads. First of all, for the patch embedding block, the 3D signals of the high-density SEMG data are divided into small patches and linearly flattened to 2D signals. These 2D signals are the main inputs for the transformer encoder because the encoder only accepts 2D signals. Then to add more capacity to the network and to embed these patches, and these 2D signals were linearly projected to another feature space. And to help the network to learn the position of each of these patches, because the transformers look at their inputs in parallel, and they do not and they cannot detect the position very effectively. So we add a learnable 1D positional embedding vector to each patch embedding block. So in this picture, the light blue ones are the patch embedded vectors, and the dark blue ones are the positional embedded vectors, which is also shown here in this formula. Here, X is the input of the patch embedded block, which is multiplied to matrix E, which is for the embedding section. And then all of these are added to a positional embedding block, and Z0 is constructed, which is the main input to the transformer encoder. The transformer encoder includes the attention mechanism, which is trying to find the similarities among all the patches that arrive at its input. To add another information, I forgot to say that as well as the patches that we feed to the transformer, in order to store all the learned information in a transformer, we add a class token at the start of all of these patches, which is shown with X0P. All of the patches are given to the transformer encoder, but after that, for the classification purpose, the information stored in the class token are used to predict the class labels. So in total, we have n+1 patches that arrive at the transformer encoder's input. And then in the self-attention mechanism that is in the transformer, we have 3 different vectors that are constructed from the transformer input. These vectors are called the keys, queries, and values with dimension D. To construct the attention weight, the dot product between the queries and keys are computed, and to make it a positive weight, and to make it a positive weight metric, we apply a softmax transformation on it, and then this weight is multiplied to values to compute the final attention metric in the transformer encoder. And in the multi-head self-attention, instead of using the D-dimensional vectors, we use the smaller vectors that are divided by edge. We have edge parallel blocks or heads in the that do the self-attention mechanism independently. And after that, all of these parallel blocks are concatenated together to construct the transformer's output. In a typical transformer, we can have multiple transformer encoders. So here shows the formula for the output of one of these encoders. After inputting the patches into the encoder, we apply a layer norm, and then we apply the multi-head self-attention. Then another layer norm is applied on the vectors, and to add the capacity to the network to work more effectively, we use an MLP layer, and there are some residual blocks here that are shown in this formula. And here in this formula, we have the final output of the transformer in the final layer, which has the patches from L0 to L1. All of the patches are outputted from the transformer encoder, but as I said before, we only use the class token called the ZL0 for the linear part, which is here shown with light blue. And this class token is given to a linear layer, and the gestures and classes are predicted. In my first work that was published in last year's EMBC conference, I proposed a very basic transformer model called the VITHGR model, which stands for the Vision Transformer Hand Gesture Recognition Model. I used only a window size of 64 samples, a patch size of 4 and 4. The depth of the model, which is the number of transformer encoders, was set to 1. I had 12 heads, and because it was a multi-class classification problem for detecting 66 hand gestures, I used the categorical cross-entropy loss function. And to have a good benchmark to compare my work with the prior works that use the same data sets, I used the 5-fold cross-validation scheme. Here I proposed 3 different models that differed in their embedding dimensions and MLP size. Model 1 was the largest, and the model 3 was the smallest one. And as you can see here, when the model gets larger, we have around 1% increase in the accuracy, but we should have as 10 times larger parameters as in the smaller models. Here I did a statistical analysis of the 3 different models. I used the Wilcoxon signed rank test, and as it is evident here, model 1 and 2 did not have any significant discrepancy between their performance over all the 19 subjects, but the other pairs of models were significantly different. And I also did another study, compared my model with a simple LDA model that used 5 time domain features and 4 autoregressive coefficients. And as you can see in the following table, the average accuracy of the LDA model for the window size of 64 was much less than the VIT-HGR models. In my other work that was published in the Scientific Reports Journal, I made an extension of the VIT-HGR model and called it the CT-HGR model, which stands for Compact Transformer-Based Hand Gesture Recognition Model. In this work, I did a comprehensive evaluation of my model under different configurations. I changed the window sizes and the number of electrode channels and evaluated my model in instantaneous training, meaning that I only fed one sample of the data to see if the model works well if it sees only one sample of the data at each time point. Here in this study, the window sizes range from 64 to 512 samples, and the number of electrode channels was set to 34, 64, and 128. The patch size differed based on the number of electrode channels, and here I designed 2 different models that differed in their embedding dimensions and their MLP hidden size. Here in this table, you can see the accuracy results for the version 1 model, which was the smaller models. As you can see, when I increased the number of channels and the window size, the average accuracy increased, but the effect of increasing the number of channels was much more significant than changing the number of window size. And here in the next table, I brought the results for the version 2 model, the average accuracy and the accuracy for all the folds of my 5-fold cross-validation. And as you can see, the average accuracy increased around 1% in the version 2 model. But here, when I compare the number of trainable parameters for both of these models, we can see that version 2 models used 3 times more learnable parameters than version 1 model, although it had only 1% increase in the accuracy. In this figure, I compared the performance of my CT-HGR version 1 for different window sizes when different folds were used as a test set. As you can see from all the figures, when folds 2, 3, and 4 of the data set, meaning that the repetitions 2, 3, and 4 of the data set were used for the test set, I had very large accuracy. But when, for example, fold 1 was used, the accuracy dropped a lot. So that is why we use the 5-fold cross-validation scheme to have a better benchmark for comparison. And in this figure, I did a Wilcoxon signed rank test and a statistical analysis for training over different window sizes for both of the models. And as it is evident, all of these models, when I doubled the size of the window, had a significant discrepancy in their performance, and it was more evident in version 1 of the CT-HGR model, in which all the p-values were very small to reject the null hypothesis. And here, in this confusion matrix, I showed the performance for version 1 model with the highest window size and the number of channels. As it is evident, you can see that it is very similar to an identity matrix, and the model performed very well for all the 66 hand gestures. And in order to make it more specific for the for different gestures, I calculated the precision, recall, and F1 score for the following matrix. And as you can see, the precision, these metrics for gestures 57 and 59 were very low, meaning that the model could not detect them correctly. Here in this picture, I compared the cosine similarities of version 1 and version 2 models for the 2 window sizes. I had 2 different results here. When for only one single model, I used larger window sizes, so I used more patches. It seemed that the model could learn. The model could learn the positional embeddings much more effectively. And also when we compare my version 1 model with version 2, for example, figure C, when the window size was set to 256, the model version 2, that was a larger model, could learn the positional embeddings much more efficiently because the because the patches that were distant from each other did not have very similarities in their positional embedding vectors, and the pictures here are smoother than those for the version 1 model. In another comparison, in another experiment that I did, I compared my CTHGR model with two different conventional machine learning and the 3D CNN model. The machine learning models I used were the SVM and LDA models that were trained with two different sets of features. The first set was based on the power spectral density features, and the second one was simple features that were used in many of the papers on hand gesture recognition, which were the root mean square, the wavelengths, the number of zero crossings, and the slope sign change. So I trained all of these models along with a 3D CNN model, which is mostly used in computer vision tasks on three-dimensional data. And because my high-density SEMG data was also three-dimensional, I assumed that it would be an appropriate model to be compared with my own transformer-based architecture. Regarding the power spectral density features that I used, I extracted these features from a recently published papers. This paper computed 5 different metrics called A, B, C, D, and E that were based on the energy of the signal and its first and second derivatives. Then 5 other different metrics from M0 to M4 were defined based on the transformational A to E features. And the final set of features that was used on that in that paper was called the M0, M1 minus M0, M2, M3 minus M2, M4 minus M3. So here in this table, I compared the accuracy results for all these 6 models, and in window sizes of 64, my own transformer-based architecture performed much better than the other models. But when the window size increased, the performance of SVM and LDA trained on the power spectral density features was comparable to my own model. And here is the statistical analysis of all these models for all the different window sizes. And as you can see, for the window size of 256, the performance of the transformer-based architecture with SVM and LDA, we did not see any significant discrepancy between their performances. But when it comes to other metrics that are used for evaluating the performance of the model, like the train time, test time, and the memory, for larger window sizes, in general, my own model consumed much less memory than SVM version 1 and LDA version 1 models. And in general, it had smaller testing time. So in general, when we consider all these metrics, the accuracy together with the train time, test time, and memory, I concluded that my own model performed better. And in another evaluation, I shuffled the whole data set on all the repetitions, because many prior works that were done on this data set did not mention their test and train faults and had very large accuracies. So when I shuffled the whole data set, I wanted to see if my model was comparable with those models. And when all the folds were shuffled, I obtained an accuracy of near 98% for a window size of 64 samples, which was very comparable to the other previously proposed models. And in another evaluation, I did an instantaneous performance evaluation, in which I set the window size to 1, meaning that at each time the transformer was faced with one data frame of the high-density SEMG signals. The performance for only 64 number of channels was very near to the performance for a window size of, for example, 64 samples, and it had an average accuracy of 89%, which was very good for this specific configuration. And in the last evaluation, I compared the performance of the model for changing the cutoff frequency of the Butterworth filter. As you can see, when the cutoff frequency was set to 1 Hertz, the model had a better average accuracy, but when the cutoff frequency of the Butterworth filter increased, the model's accuracy declined. In my next work that was published in this year's ICAST conference, I tried to integrate HDSEMG decomposition with high density imaging. There are some blind source methods, the motor unit spike trains from high density SEMG signals. And these motor unit spike trains that are sparse estimations of motor unit activation times can be largely used for neuromuscular conditions and electric pattern recognition. So because high density SEMG signals were spatiotemporal convolutional motor unit spike trains, I assumed that they could give me an exact physiological description of how each hand movement is done, and they provide me with some generation details of different hand gestures if they are combined with high density SEMG data. So here, if we consider the multi-channel SEMG signals as a convolutive mixture of the discharge timings of multiple motor units, we can have the following formula in which the capital X is the capital X shows the recordings of all M electrode channels, which is known to us, and capital S shows the motor unit spike trains of the N extracted sources, which is unknown to us, and matrix H is the matrix of action potentials, which is still unknown to us. So for solving this problem, we should extract some sources that are not fully correlated, meaning that they should be either independent or sparse. So to make it feasible, we have to extend the source vectors with their L-1 delayed versions to have many samples of the sources to make sure that all these samples are not dependent on each other. And to make this problem solvable, we should also extend the observation vectors with their T-delayed version, which results in this following matrix formula. So the blind source separations used in this context, the most popular ones are the GC-COSY method and the fast ICA method. In the GC-COSY, called the gradient convolution kernel compensation, we try to estimate the motor unit spike trains with the linear minimum mean square error, such that we have S hat, which is the estimate of the motor unit spike trains, as the product of two correlation matrices. The lower score C shows the cross correlation between the motor unit spike trains and the observations, and the capital C shows the autocorrelation matrix of observations. And in the other approach, which is the fast ICA method, the goal is to estimate some separation vectors W, such that these W vectors, when multiplied to a Z matrix, which is the White matrix of observations, gives the estimated motor unit spike trains. Here in this work, I used the combination of fast ICA and GC-COSY methods that was proposed in a popular paper before. With that one, when I had the raw high density SEMG data, I extracted the motor unit spike trains using that combination of algorithms. And then with the spike triggered averaging method, I estimated the motor unit action potentials, and then I calculated the peak to peak values of these motor unit action potentials. And because the number of iterations in the blind source separation that I used was set to 7, I had a maximum of 7 independent sources. So I had a maximum of 7 peak-to-peak motor unit action potential values. Here in this picture, you can see the motor unit action potentials of a single motor unit for all the 128 channels. And these two pictures show the 2D and 3D representation of the motor unit action potentials, the peak-to-peak motor unit action potentials that are fed to my hybrid model. Here, I used two different transformers. The first one was the CTHGR version 1 that I explained about before. It was trained independently with raw high-density SEMG signals. By raw, I mean the high-density SEMG signals that were pre-processed, normalized, and low-pass filtered. And the other transformer model was trained based on the peak-to-peak motor unit action potentials. These two models are trained separately, and then their class tokens were combined with each other and given to two fully connected layers for final classification. So in the first stage, these two models were trained separately, and then the parameters of the models were frozen and remained constant. And in the second stage, I had only two trainable layers that were the fully connected layers that were applied on the combination of class tokens of these two models. Here I brought the accuracy results for my fuse model. As you can see, the results improved much in comparison to two stand-alone models, and also seeing the results for the statistical analysis, we can see that all these three models differed significantly in their performance because the p-values here were very small. And in the final chapter of my work that is going to be published in this year's SMC conference, I wanted to apply a very different model that was based on spiking neural networks that do gesture recognition in an event-based fashion. By event-based fashion, I mean that we have some specific activation functions here that use only discrete valued spikes that are only 0 or 1. By this, I wanted to imitate human brain's cognitive function with biologically inspired models of neurons and synapses, which makes it more biologically explainable and computationally efficient because it only works with 0 or 1 values and not with large, complex, and continuous values. These spiking neural networks were widely used in image classification, object tracking, and gesture recognition using images and videos. But there were limited works in the context of EMG-based gesture recognition. So I was motivated to test this on my high-density SEMG data to evaluate its performance. The specific neuron type that I used here was the leaky integrate and fire neuron, in which the membrane potential is dependent on three different factors. The first one is the membrane potential, the previous time step, and the input current, and the activation status of the neuron in the previous time step. Here I show the structure of my SNN-based framework. I used only two linear layers and a window size of 128, and I wanted to only classify 14 gestures of my data set that contained only 1 degree of freedom. So in each time point, I inputted a total of 128 samples to the network, which was the signals for 128 electrodes, and then defining a specific softmax function for discrete valued signals. I defined a cross-entropy function, a cross-entropy loss function, which is called the cross-entropy rate loss function, that is mostly used in the context of spiking neural networks, in which at each time point, we estimate and calculate the number of spikes for each hand gesture, and then we sum the number of spikes for all the hand gestures, and finally, the gesture that has the largest number of spikes is predicted as the correct class. Here in this table, I showed the accuracy ranges that I obtained for different subjects. The accuracy the accuracy that I had a very large range from 40 to near 100%. 6 of my subjects had a very good accuracy from 80 to near 100%, but the other subjects did not work well with the SNN-based frameworks. And here shows the statistical analysis for using different sessions or repetitions of the data as the test set. As you can see, when we used sessions 2, 3, 4, and 5, there is no significant discrepancy between the performance of the model over 19 participants, but when fold 1 of the data set is used as the test set, the performance of the network drops a lot, and it is very different from the performance in other test folds. And here at the right side, I showed the raster plots of the output spiking neurons for subject 16, which had a very good performance. The accuracy ranged between 80 to 100. Here in this plot, for gesture 11, we had the largest number of spikes, and this gesture was exactly detected as the correct class. And here in another window of the signal, gesture 3 had the largest number of spikes in all the time steps and was detected as the correct class. Now my presentation ended. I will give some conclusions, some main conclusions of my works, and then I will give some future research directions. First of all, as I said before, the accuracy for all the folds and the average accuracy increased by increasing both the window size and the number of electrode channels, but the effect of increasing the number of electrode channels was much more considerable. Choosing which repetition as the test set played a vital role in the reported accuracy, and that is why we use the 5-fold cross-validation scheme in all of our works to have a good benchmark. And also using larger transformer-based models did not make any significant difference in the accuracy. It only made it more time-consuming and energy-consuming, so it was not suggested to make the transformer-based model very, very large. And also using more patches helps the network to learn the positional embeddings more efficiently, and making the model larger again makes the network learn the positional embeddings more efficiently. And in brief, when I compared my CTHGR model with conventional ML models for small window sizes, I had the best performance of the CTHGR model, but for larger window sizes, I did not have very good accuracy compared to the ML models. But when it comes to the time and memory of the system, the CTHGR generally outperformed the machine learning models. And also when I combine, when I combine the high density SEMG signals with motor unit spike trains, I have a very significant improvement in the performance of my network. And regarding the SNN based models, it is very dependent, the accuracy of the model is very dependent on the utilized repetition and also the subject from which we collect the data. And as some future research directions, it is better to use a more generalized data set that is for hand amputees, because the data set I used was only acquired from able-bodied patients. And another important approach would be to design a deep learning-based architecture for extracting the motor unit spike trains instead of using the blind source suppression methods to be used in real-time HMI devices. And also we can improve the performance and generalizability of the SNN frameworks by using transfer learning approaches, because SNN frameworks in many of the contexts require too much time to be trained. So using transfer learning improves their performance much better. And also it would be good to combine spiking neural networks with CNNs and RNNs, and also with different kinds of spiking neurons rather than the leaky, integrate, and fire, to evaluate their performance on our utilized data sets. And here are the references that I used for this thesis defense. The first one is for my high density SEMG dataset, and the other 4 ones are for the conferences and the journal paper that I worked on during this thesis. My presentation finished. Thank you all for your attention and consideration.